here. Let's focus on where the changes are, and that is in the mass spec acquisition aspects of things. So if we click here, this is what your mass spec acquisition window will look like. And essentially what we have, the first thing we need to do is give it a tune file. So we'll go ahead and say, let me select my list. And I want this tune file here, open. If I want to see what those tune values are for that particular tune file, I could go ahead and click on this magnifying glass here, and it'll give me all the conditions for this particular tune file. So I know that I'm in positive EI mode, my repeller voltage, all the parameters for the mass spec are here, and they're telling you, okay, this is what I'm going to be operating under. It tells me that the system was tuned at 280 for this particular analysis. And that's another thing that I would like to point out. Most customers are the default on the source temperature from the factory is 230 degrees. However, as you'll notice through method development, you'll notice that varying the source temperature may give you better sensitivity and peak response for the heavy eluting compounds, as long as there's no degradation. And the source in the 5975C and also the triple quad and our GCQ top all go up to 350 degrees C. So that's a method development parameter that you may be not using the total power of. So that's something to keep in mind. Okay? So if you want to change the source temperature from what was currently tuned, you could do so here. However, I recommend that you tune at the temperature that you're going to operate your mass spec. So if I were to change this to, let's say, 300 degrees, I would probably want to go ahead and tune the mass spec at 300 degrees just for consistency purposes. I'm going to leave that to a 980. Okay, again, 70 electron volts for the electron energy. That has not changed. If you want to set up a solvent delay, you can do that here, whatever that may be. You could have the mass spec acquire for only 1 minute. However, if you leave this box unchecked, the mass spec will acquire for the duration of the GC run. Okay? Peak width and time filtering. If you want to apply a smoothing function to your peak, or Gaussian smoothing functions, during acquisition for display purposes, you could go ahead and apply a peak width here in seconds, in this case 1.2, and this peak width is usually the peak width at half height of your narrowest peak in your chromatogram. So essentially you have to make one injection, find out what your narrowest peak is, and at the full width at half height of that peak, you enter that here. And you can choose not to use the time filtering and just collect the raw data. That's totally fine as well. In terms of detector setting, one of the things that we have found is that to ensure longer lifetime of your electromultiplier, to ensure greater linear dynamic range, and also to ensure that you transfer methods from one instrument to the next more efficiently, using a detector setting of a gain factor will give you that capability more efficiently. And versus most customers use a delta EMV, and if you use a delta EMV, it's essentially, you can, let's say, for example, you have a delta EMV of 200, it'll add 200 to your multiplier from your tune values, okay? But we recommend that using a gain factor will be more beneficial to for instrument to instrument method transfers. Okay? So here now what we could say is, what mode of acquisition do we want? In this particular case, we'll start with a full scan. If you're developing a method of a compound for, in this particular case, a triple quad method, you always have to start with a full scan. And we'll have a solvent delay. In the drop-down menu here, we'll select MX1 scan. We have a gain factor of 5. Depends on your how low the levels. Typically, what I find is a gain factor of 10 is more than adequate to give me required sensitivity. You could crank up the gain to 100, however, noting that you will pay the price in terms of more noise, and also you may have less dynamic range by doing so. A gain factor of 10 keeps your multiplier at a good range for analysis at the low level. But typically for method development purposes, I like to work at about a 500 ppb standard for method development purposes. So we'll set the gain at 1, and that should be adequate. Here, we'll go ahead and call your full scan, your segments here. So if you want to have a full scan segment, you're going to start at mass 50, for example, to 575 or whatever your end mass is. Now, a lot of customers ask me, Rafael, what scan time should I use when making an analysis? How many milliseconds should that be? The rule that I found that works the best is to use a scan time such that you have between 3 and 5 cycles per second in this particular window here. And what this does is it gives you the best of both worlds of you get the sensitivity required, you get the reproducibility, and you also get the adequate number of scans across a peak. So what I do is I try to make this value such that I have between 3 and 5 cycles per second. So the 275 in this case is adequate. If you go ahead and say, you know what, I want to go ahead and do 50 millisecond scan time, and now you have 12 cycles per second. There's nothing wrong with doing this. However, you may be oversampling your data, and you may have too many data points across your peak, which makes the data files larger, and you may not be gaining any more by having more data points. So therefore, you may lose some sensitivity. So you want to find that sweet spot that gives you between 3 and 5 cycles per second here. Okay. The other mode, for example, if you want to go ahead and say, you know what, I want to go ahead and create a sim method for my analysis, you could go ahead and MS1 sim. And now here you will type your compound name, whatever that is, compound 1. What mass you want to sim on, let's choose, for example, 272, and the resolution on the quads, unit being 0.7 resolution, wide 1.2, and wide is 1.7. And you can define those values from the tune, and we can show you how to do that later on. Okay? So again, what dwell time do we use? We want the cycles per second to be between 3 and 5. So if I want to go ahead and add another scan segment, it's going to be compound 2. And again, this is the sim window here. And this window, for example, we want to say is going to be mass 154. If you notice here, since I have 2 ions, now we have half the number of cycles per second, so on and so forth. You get the idea. So I go ahead and fill down here, and now every 3.3 cycles per second. So typically, you have 2 choices between 3 and 5 cycles per second. Some of my colleagues used equivalent to around 300 milliseconds per cycle. So either or, you have options, but that's typically a good rule to follow, a good guideline. Again, nothing is set in stone. It's just best practices. However, in this particular case, we have a triple quad. So if we want to go ahead and create a product ion analysis and find out, okay, we have our full scan, we have some ions of interest. Now we want to go ahead and create a product ion scan. So for compound 1, for example, now we have a precursor of 272, MS1 resolution for quad 1, because it's a triple quad in this particular case. And we want to go ahead and monitor that to mass 184. Again, this is experimentally determined. We're going to actually product scans. We're going to go from 50 to 300. So essentially, what we're doing is we're saying take mass 272, pass it via Q1, okay, and then in Q2, you have a collision cell. Q2, monitor masses 50 to 300 after we hit mass 272 with a collision energy of 25. So essentially what this is doing is taking 272, hitting it with some energy, and then monitoring on Q2 masses 50 to 300. Again, there's a product ion experiment that we use for MRM method development parameters. Again, we have some automated tools that will facilitate creating these types of methods so that you can vary the collision energies as such so you can optimize those. So the workflow would be after you have your product ions, go ahead and set up your MRMs, multiple reaction monitoring. For example, compound 1, 272, and you may find that it has a product ion at 184 for compound 1. Set up the MS2 resolution, too wide, and again, taking a look at the cycles per second here, you probably want to go ahead and say 300. That gives me between 3 and 5, 3.3, about 300 milliseconds per cycle. And then you can go ahead and add a new segment and have multiple MRMs in this particular time window here for MRMs. You could also go ahead and say, you know what, I want to add a different time segment, time segment, and say from time segment starting at 5 minutes, I want to look at other compounds. You go ahead here, compound 3, compound 4, and if one of these is your internal standards, you go ahead and label it here. The benefit of labeling things here is now that when you go ahead and do your quantitation later on, if you're going to quantitate, this particular compound will be flagged as an internal standard already, and this will be from your mass spec acquisition. Okay, so you can set that up in that manner. So as you can see, it's very straightforward, very clean interface for setting up your scan, SIM, and MRM parameters. You also have the options, of course, to do precursor ion experiments, neutral loss, and neutral gains. So we won't go over that in this particular session. Okay? I'm going to have to say, okay. All right? But